short announcement. So today, after the lecture of we are going to have a poster session on our Okay. Okay. So now we have Raphaël again for this second lecture.
Okay, thank you, Ale. Good morning, everyone. So we're gonna pick up where we left off yesterday. So if you remember, we had introduced these generalized cycles, which were a homology with local coefficients that were defined from a differential system, right? That was a connection acting on matrices, okay, or matrix-valued functions on a punctured sphere. And okay, so today the lecture is going to be a little bit more technical. So we're going to prove some results, and we're going to start by writing down the proof of the generalization of the Riemann bilinear identities. So this is what we ended yesterday's lecture by writing. So let me just write it again. And somehow, so what we will do in the subsequent steps is to, so once we have this technical result, so why will we go through the proof actually? So it's a kind of technical proof, but the reason is that the techniques that will be involved in that proof are basically the same techniques that will come over and over again to prove all the results that we will need. And by the end of the lecture, we will define a certain function, okay? And that function somehow is the main player of the whole lecture. And so even though we won't have time to really discuss its deep properties, we will see in the exercise sessions that it's supposed to resum the partition function of topological recursion. And it will have many connections to other fields, such as conformal field theory, and so on. Okay, so first, are there questions on what we did yesterday? Yes.
You said H bar to 1.
Yeah.
Introduces dependence on H bar is complicated, or it's a little bit.
Well, so actually it's not complicated at all, right? Instead of considering connections, you can consider H bar connections, right? And run the same constructions through, right? And then the question that you can ask is, or a natural question would be, what happens when you actually send H bar to 0, right? Or in the vicinity or the asymptotics when H bar is approaching 0, right? And then this has to do with the singular perturbation of the differential system. Well, then you can look for WKB solutions and see what happens. And this is actually how you relate this story to topological recursion, right? But so in topological recursion, you had some objects which were these omega GNs, and somehow if you sum over the genus, you can define some WNs, which have natural definitions in the context of connections or even H bar connections. But so we won't have time to get into these details, but we can discuss it anytime. Okay, any other question? All right. So yesterday we left off on these Riemann bilinear identities, and they were taking this form. So the integral over the boundary of C gamma. So if you remember, C was this punctured sphere. Okay, so it was basically E1 with some marked points actually, and on this we had drawn some graph. Okay, so P, say J, all right. Okay, so that was the graph gamma, such that if you remove gamma from P1 minus these points, you had something simply connected. Okay, so now if you remove gamma from P1, what you actually get is some kind of polygon, if you wish. And this here, the boundary of C gamma, denotes the boundary of that polygon. Okay, so what does it look like? So for instance, if we had a sphere with 4 marked points, then when you open it, what happens is that you have something that looks like this. So P1. Okay, then let me give names to these points. Let's say A and B, the 2 vertices. Okay, so then you go from P1, then you go to A. Okay, then you go to B. Then you go to another point, which was, say, P4. Okay, then you go back to B. Then you go to P3. Okay, then back to B. A. P2. And anyways, I didn't do it correctly. So P3, B, A, P2, A again, and then P1. So let's do it here. Okay, so C, where you remove gamma, would look something like that. Okay, and then you can imagine that these things have to be glued together to form the surface again. Okay, so many times what will happen is that we will consider some integrals somewhere inside. We will push the contours out to the edges of that simply connected domain. And then basically, since you will be integrating on one side and then on the other side of such edges, if you have objects that are meromorphic or rational on the surface, then you can actually compare quite precisely what happens on one side or the other. And so this will be somehow, so you will see this will be an argument that comes over and over again in all the proofs, okay? All right, so what did we have? We had this trace of omega 1 F2, okay? So recall that omega was a matrix valued differential form, and the F's were primitives of these differential forms defined on tubular neighborhoods of the boundary. So basically the tubular neighborhood looked something like this. Okay. And where maybe inside we were leaving off the poles of the omega i's. Okay? And the content of the theorem tells you that if you calculate this, this is actually equal to minus the integral of the same expression, but where we exchange the indices. So this is now F1 omega 2, okay? And this was written as a bilinear expression in the periods of these differential forms. So periods in the sense of the pairing between matrix valued differential forms and cycles with local coefficients. And so this was something like a sum over KL from 1 to G, which was the dimension of the space of cycles. The integral over AK, omega 1, integral omega 2 of AL. And here there was something which was the inverse of the intersection matrix, where these IKL are defined by this intersection with these AKs being a basis of H1 hat nabla. Okay, so before we prove it, are there questions about this formulation here? Okay, so omega I was a matrix valued anamorphic one form with omega I is dFi, okay, where the Fi's are only defined on the tubular neighborhood. Neighborhood. Yes. How did I do the polygon? Okay, so I just started from P1 and I followed it on one side. So P1 to A to B to PM, here it's M with M equals 4, then back to B, and so basically I just follow the thing here. Yeah? Any other question? All right. So, okay. So basically this boundary here is, as you can see on this polygon here, is the sum along the edges of yeah, I've been calling it gamma, but actually this letter is epsilon. So anyways. Okay, so it's a sum along the edges, right? And you see that every edge will be glued to the other one, right? So if you go along, every edge will appear twice, once in a certain direction, and the other one, and the other time in the other direction. So it's something that you can write E plus, yeah, minus E minus, right? Where E plus is one side, E minus is the other side, and you have this minus sign for the direction in which you go along. Okay, so just starting from this expression here, you do something like this, trace, F1, F2. Okay, so this now is the sum over the edges of epsilon of this trace here. Okay, and so basically you have to be a little careful. Like if you're integrating matrix value differential forms, you can integrate them on generalized cycles which belong to that H1. Okay, but here, so this is a honest contour on the base, and this here is not matrix valued, right? It's scalar valued. So every time I'll try to be careful to write things in a way that respects this thing. So for instance, I'm not going to integrate a matrix value differential form on a contour which is on the base, right? That wouldn't make much sense. Okay, so this you can just replace with that. So now this is the integral over E plus minus E minus of the trace of omega 1 F2. So the trace of that product, to compute it, what you can do is decompose omega 1 and F2 on bases of matrices. Okay, so I'm going to introduce, say, E1 to En squared, the basis of the matrices, as well, basis of matrices. So these are n by n matrices, as well. Good point. So capital E, yeah, good idea. Okay, n squared, base of matrices, and E with upper indices 1, 2, En squared, the dual basis. Okay, and so this dual basis is just defined by the requirement that trace of EI EJ be delta IJ, the Kronecker delta. Okay, so with that means that we can write this trace here as, so sum, just an epsilon, basically as the product, so E plus minus E minus of now the sum from I equals 1 to n squared of, so basically the trace of omega 1 E I times the trace of F2 E I. Okay, and now the point is that the omega 1s were matrix value differential forms on the base. So they are meromorphic in the sense that they have the same value on both sides of a given edge. Okay? The functions f, however, don't have the same value. And actually, the difference between one side and the other of f2 is exactly omega 2. So which means that this can be written like that, sum from I equals 1 to n squared, okay? Okay, so here, basically, this trace here has the same value on both sides. So if you wish, what we can do is basically, since you have a minus sign here, you can do E plus times this thing here, trace omega 1 EI, trace F2 EI, okay, minus E minus trace W1 EI, trace F2 EI. Okay, so here I haven't done anything special, except that the value of this integrand here on the E minus sign, okay, is actually the, so this first part has the same value on E plus, so you can replace E plus as far as this first term is concerned. But for the second one, right, the difference between the value of F2 on E minus and its value on E plus is the integral of its differential. So this, which means that this here, h epsilon, I equals 1 n squared, right? Now this is E plus, trace omega 1 EI, okay? And this difference here, you can replace by the integral along gamma E, right? So remember, gamma E was the, so if this here is E, gamma E was this contour going around here. Okay? And here now of trace omega 2 EI. Okay? All right? And basically, you see that this here expression is linear in omega 1. Okay, so so basically this can be written, at least formally for now, as the integral of omega 1 on a certain cycle that I call gamma of omega 2, where where this gamma omega 2 is exactly what you think it is. So it's gamma of omega 2 is now the sum over the edges. Okay. And you have E plus tensor EI. This is E plus tensor EI. Okay. So this is a chain weighted by a matrix. Okay. Times the numbers that appears, which are these, which are those? Up, gamma E, trace, omega 2, EI. And there's a sum over I also. Okay? Now, to write something like I did here, okay, like meaning that I have this form and I have paired it with this gamma omega 2 defined in such a way, that means that the boundary of this gamma omega 2 has to vanish. Okay, because otherwise you can't pair it with a matrix value differential form. Okay, so we have to calculate the value of its boundary and check that it's 0. Okay, so what is it? Right? You remember how we do that from yesterday's definition? So this boundary operator was the boundary of the chains downstairs, and basically you had to take the value of the matrix at the initial point and the value of the parallel transported matrix at the final point with sign. Okay? And so, since we're summing over all the edges, the initial and end points will either be vertices or some of the PIs. And since the homology was defined relative to the PIs, you drop the PIs, and so what you're left with is a sum, okay, over now the vertices. So vertex of epsilon. Okay, you still have this sum over the index I. Okay, and all right, and now this takes form of the vertices, okay, weighted by the sum, right? Each vertex will have a certain number of edges that come in that direction, and so you sum over all the edges that are basically around the vertex V. So I'm just using this E arrow V notation, but I hope it's clear what I mean. Of basically, now you had this sum over I. So this is now the integral of gamma E, and you have this sum over I of EI trace omega 2 EI, and this is just omega 2. Okay? So it's very tempting to write omega 2 here, but this is a chain on the base and not a generalized form. So let's write it this way: V tensor EI, okay, weighted by this number, which is the sum of trace omega 2 EI. Okay, and now you can notice that here we have only one function, and we are taking this combination of integrals. And since for every vertex, the sum of the paths, so, okay, so let's make this way, so it's V, so they were all trivalent vertices. Okay, so if you take the sum of the gammas, right, so it goes behind the surface and comes back. If you do the sum of all, like that, 1, 2, and 3, if you do the sum, then you get something that you can close behind. Okay? So this is 0. And then the sum is 0 as well. And this implies that gamma omega 2 belongs to H1. Okay? So these steps, we're going to do them basically over and over again. You want to compute an integral, you push it to the edges, then you have E plus and E minus. You can compare two sides with some kind of monodromy argument in such a way. Then you get some cycles. You have to check that their boundaries vanish, and yeah. Okay, so that's kind of technical, but we need that. Okay, so it's justified to write it this way. Okay, are there questions about these few steps? Okay. So let's continue. So now, since it belongs to H1, we can decompose it on the basis that we have considered. Okay, so we can write gamma of omega 2, and we can decompose it as a sum so basically over the A's, and you can write this such a way. So the coefficients, you write them ck of omega 2, ak, this from 1 to g. All right, and okay, and the skew symmetry, right? So what did we have? We had this not written anymore. So we had this integral like this with trace of omega 1 f2. Okay, and you can integrate by part. Basically, the usual argument to see that this is minus the same thing where you've reversed the 2. So f1 omega 2. Yeah? Okay, so so yeah, okay, and this means that so since this was also equal to that there, okay, so this was the integral of omega 1 gamma omega 2, this now is equal to minus the integral of omega 2 gamma omega 1. okay, which means that we can decompose now CK, okay, because these CKs, these functions CKs, they are now linear forms on the matrix value differential forms. So they are cycles. So CK can now actually be decomposed as a sum over L from 1 to 2G of CK comma L, AL with CKL is minus CLK. Okay, we introduced the matrix value differential forms as objects that could be paired with the generalized cycles, okay, which exactly means that there are linear forms on them. And here we're using the converse argument that linear forms on the matrix value differential forms are cycles. Okay, so that's the kind of a game that you play. Okay, so all right. So now we have these CKLs, which are basically, so if now you replace in that expression here, you see that this integral, these two integrals that we're trying to compute are eventually the I'm going to erase this. So basically now the rest of the proof consists in showing that this matrix C is the inverse of the intersection matrix. Okay, so if you remember, the result of this in the statement of the theorem was a bilinear expression in the integrals of omega 1 and omega 2 on the basis, and these in the bilinear expression involved the inverse of the intersection matrix. And basically, so now we have to show that this matrix C is that inverse. Okay, so we define the sum KL 1 to 2G. Now we have CKL of AK tensor AL. Okay, and this we can write as this the sum of E plus CR the edges gamma E plus tensor EI. Okay. So we sum over I as well. This was capital I, and then we have gamma E tensor EI. Okay, so all right, so these basis elements, the AKs and ALs, okay, so they are linear combinations of chains on the base weighted by matrices. Okay, so I'm going to repeat that over and over again. So there are two. So now what you can do is homotopically deform the chains on the base in such a way that that an element of the basis AK can either be written as a sum over the edges of the graph. Okay, so then you can write this as, say, E tensor some coefficients. So maybe we can call them how can I call them? Maybe A, K, comma E. Okay, but you can also homotopically deform them such that the chains on the base, instead of being along the edges of the graph, be along the edges of the dual graph. And the dual graph is made of these gamma E's here. So it's still a sum over the edges, except that now you have gamma E tensor some other coefficient that maybe I can write B K E. Okay, so on the right hand side, after the tensor product, these are matrices, right? Chains weighted by matrices. So if you write it in such a way, if you have these two ways of decomposing it, then you can take the intersection of AK with AL, intersected with AL, okay? And since now, by definition of the dual graph, gamma E only intersects the edge E in one single point, okay? Then this becomes the sum over the edges of epsilon. Yeah, I think sometimes I keep saying gamma, I'm not sure. Of now the trace of A, K, E, B, L, E. Okay, and that was I, K, L, the intersection matrix. Okay, does that make sense? Okay, so the AKs and ALs, they can be decomposed either on the graph epsilon itself or on the dual graph. And by using these two homotopically equivalent ways to describe the cycles, you can actually calculate their intersection in a very easy way. And you just get this, this form for the intersection matrix. Yes?
The intersection matrix
So, okay, we will, you will believe me for now, okay, and we will construct a basis of the space of cycles in the exercise session, such that the intersection matrix is basically, such that this basis is the Darboux basis for the symplectic form that it defines, and so it will be non-degenerate. So it's not obvious, but you can just calculate it in a certain basis and find that it's non-degenerate. Okay, but thanks for the question. No, we'll see that in the exercise session when we actually finish constructing the basis that I had started discussing yesterday. Okay. Okay, so you see this gamma here, it belongs to the tensor squared of H1. Okay, this intersection here is a bilinear on H1 tensor squared, and we can upgrade it to an intersection product on the tensor squared of H1. Okay, take this guy. So it's on H1 at blah blah tensor squared. Okay, and you can upgrade it to say something that so intersection hat and with a little tensor product underneath on H1 nabla tensor squared tensor h1 nabla tensor squared. Okay, by intersecting the first and the third and the second and the fourth components. Okay. All right. Okay. And so in particular, we can calculate AK tensor AL, and we can intersect it with gamma. So gamma is this thing here, right? Okay. So what do we get? First and third, second and fourth. Okay. So the first and third will give us, so now have a sum, make some space here. Okay. Okay, so you just have to expand gamma, right? So we have KL. Okay, so now K goes with the first index. So say this is the, so actually I'm going to write them maybe P and Q. Okay, so we have the sum over K and L from 1 to G. All right, then we have AP intersected with AK, so that's IP comma K. Then we have CKL, and then we have IQL. Okay, so just to be clear, so this is what this generalized intersection on the product looks like when you take the basis elements and you intersect them with the gamma we have here. All right. So now if we use basically the expression for IKLs that we have obtained from the formation of the AKs and AL, what we get is, well, I want to get it right. So this is now a sum again on the edges of gamma. All right. Okay, so we have a sum over the basis elements, and now this is AK intersected with E plus tensor E I. Okay, times AL intersected with gamma E tensor E I. Okay, where this first one here is just obtained by directly calculating this intersection, and the second one is obtained by this second expression of gamma here, where we had E plus EI and gamma E EI. Yeah. It's P and Q. Yes, yes, of course, of course. Thank you. P. Yep. Okay. All right. Now we can take for AP this expression, and we can take for AQ this expression to calculate these intersections. All right. So now this AP, you look at its homotopic deformation to the dual graph to intersect it with E plus in an easy way. And AQ, you look at its homotopic deformation on the graph epsilon to intersect it with gamma E. Okay? And this gives now, so same on the same line. This is now equal to, so the sum over the edges still have this sum over indices here. Okay. Now AP intersected with E plus gives you BKL product with EI and traced. This is now the trace of B. So it's not a K, it's a P. BPE times EI times the trace of AQE EI. Okay, so going back and forth between different representations of these cycles, you get this expression here. Okay, now the sum over I of this trace times this trace, by definition, is just now the sum over the edges of the trace of B, P, E, A, Q, E. And now you should have stopped me because there's a sign error. Because this AP here gives a gamma E, and so gamma E intersected with E plus, by definition of the dual graph, gives a minus sign because of the orientation. So here, there's a minus sign. Here, there's a minus sign. Okay, but now you recognize this expression, sum over the edges of trace of B times A. It's nothing but the intersection matrix with a minus sign. This is now minus I and I want to get this right. So PQ, now P and Q, QP. Okay, thank you.
This already obvious.
Sorry, second.
Just look at the
Uh-huh.
using the IC
No, I want to prove that C is the inverse of I.
Ah, sure.
Yeah, which we're getting to right now. No, exactly. No, that's the point, right? Because somehow we almost have the result up to finding out that this C matrix is the inverse of the intersection matrix. Okay, so PQ, GL, okay, all right. So now, KL, okay, so Q and P. So now I think I still got this sign wrong. So let's see. So what do we have here? Here we have I, C, and I transpose, which is minus I transpose. Okay, so let's gather this together. Okay, so we have PK, KL in this. So this is I times C times I transpose, which is equal to minus I transpose, okay, which is I, okay. So I believe there is a sign error. Okay, so how can I deal with that? All right, so PQ, P, CKL, IQL. All right, so this was a P plus, so here there was a minus sign. E stuff, BA, minus. Well, okay, that's life. So, okay, so I transpose equals I. So up to invertibility of I, which we will see in the exercise session, what you get here is that C is minus the inverse of I. Okay? And so up to a sign that I'm not figuring right now, we get the result that we wanted, and this ends the proof. Okay? All right. Are there questions about this? Okay, that's a lot, I think. But yeah. Right, so the key is that intersection product on the tensor squared of H1. Questions? Okay. Deforming the basis on the graph, on the dual graph, taking intersection on the tensor product, and well, this trick basically, which is to calculate in two different ways the intersection of gamma, which was this bilinear, right? This basically tensor product whose coefficients was these CKLs, right? Calculate this in two ways, the direct way and the second way using the homotopically deformed cycles, compare the two results, and this gives you the matrix C. All right. So basically, in this proof, you have all the techniques that you need to do all the rest. Well, actually, so there's a way to reabsorb the sign. Okay, it's that. So I had written trace of omega 1 f2 over this. Okay, equals to minus the same f1 f2 equal to sum KL periods omega 1 K I KL minus 1 integral omega 2 AL. Okay, so what we proved is just this 2 1. Okay, so somehow I believe there was no sign error in the proof. I'm just changing the statement. All right, so there's a corollary of this, is that for any matrix value differential form, you have something that you can call quantum Riemann bilinear inequality, which is that this I over 2 sum KL equals 1 to G, and it's basically the same expression KL minus 1, except that you replace the second form with the complex conjugate of the first one. Okay, so we'll see that in the exercise session. It follows directly from this one in the exact same way that you would do on Riemann surfaces. Okay, and then from this inequality, okay, you can show that a natural period matrix that you can associate to the quantum spectral curve has a positive imaginary part. Okay, so I'm just mentioning it here, and we'll talk about it this afternoon. Okay, is it clear why there should be an I here? Right, this is anti-symmetric. So it basically takes the form, if you were in a Darboux basis, you would have an expression minus its complex conjugate. So It has the I factor, multiplied by I, get a real number, and this is what you can compare to 0. Okay, and that's, and the proof is exercise. Valued in matrices, yeah. So matrix valued meromorphic one form. Okay, so definition. So you've seen that in topological recursion you have these this input, which is so you have this spectral covering, which is the covering of Riemann surfaces, and you have this omega 01 and omega 02, which are the first two objects that you need to run the recursion. And so in the context that we have here, we will define a W1 and a W2, which are generalizations of those in that context, and whose leading orders, when you, for instance, introduce an H bar and look at the H bar to 0 asymptotics, give you the input of topological recursion. And okay, and so we start by W1. Okay, so W1, it takes as input a point on C. Okay, without so I don't think I had given that a name. So CP, which was C minus the poles of the differential system. Okay. Well, so it is. Good thing you're following, actually. Okay, comma E, right? Where E is just a matrix. This is now the trace of phi of x times m of x comma E. Okay, so let me remind you, we had the differential system in the form dm is phi m. Okay, and we were generically solving this xe as psi of x e psi of x minus 1, okay, where psi was in fact the solution of deep psi is phi psi. Okay, so omega 01 in topological recursion, it's a one form on the spectral curve, on the classical spectral curve. And here, this W1 is, in some sense, a differential on the quantum spectral curve. It takes as input this x comma e, right, which is basically the data you need to define this m, right? And you take the trace. So somehow it's in the dual. Okay, and since I don't want it to be in the dual, I am basically no, okay, I'm going to leave it this way. Okay, W1 is just this element here. Okay, so trace phi was the connection potential, if you want. So the basically defines the differential system, and m is the solution of the matrix version of this one, and we write it in this form. Okay, so that's it. All right. Okay, so I'm just saying that if you wanted to look at what happens to W1, say, if you introduce an H bar and send H bar to 0, what you would have to do is look at the leading order of phi and calculate what M looks like if you look for psi in certain forms, right? So usually you do WKB asymptotics. You have a group valued version of it, and then you can replace here, replace there, calculate the expansion, and keep the first term. All right, so now we are going to discuss deformation. Okay, so far, if you wish, everything was discussed point-wise as far as the differential system was concerned. Okay, and so now what happens? How do these generalized cycle, or what do they have to do with deformations of the data we started from? Okay, and this takes the form of the following map. Okay, you can call gamma, right? Which basically, if you consider a deformation of the data we're starting from, so basically a deformation of phi. Okay, then you can define the following object, which is the sum over the edges of the graph epsilon of the edges tensor. Okay, and so now you need a matrix, right, to weight these chains, and this matrix is the deformation of the monodromy of the connection times its inverse. Let's keep them fixed for now. You can also, I mean, it also works. You can also move the PIs. And yeah, let's keep them fixed for now. Because, so what we're doing here is to associate the deformations, something that I will argue in a minute is an element of H1. Okay, so is an element of H1 hat. Okay, and so this will establish a correspondence between deformations and generalized cycles. Okay, that being said, with the types of cycles we've allowed, we don't get deformations or variations of the positions of the poles of the connection. Okay, so you need to do something more, but this can be done as well. And even more generally, if you are not on P1 but on a higher genus Riemann surface, you can not only deform the positions of the poles, but also the complex structure, right? Which here for P1 is just basically the positions of the poles.
Are you thinking also the connections being deformed? I mean, you said that
yeah,
you want to keep the poles fixed.
Poles are fixed, but the other moduli can vary.
Okay.
And the other moduli in this context are just basically the residues of the poles. Okay, so why is this object here an element of H1? Okay, so how do we do this? It's the same. We just compute its boundary, right? Gamma delta. Okay, so this becomes the sum over the vertices of gamma V tensor. And this looks like the one we had before. Now it becomes a sum of all the edges adjacent to the vertex of whatever we have here. Gamma E dot S gamma E minus 1. Okay. Now this here is 0. Okay, and so why is it 0? Okay, so it's actually the exact same reason as before. So what we said before was like, if we have a vertex and we do the sum of the gamma e's corresponding to the edges around the vertex, right? So this is gamma E1, gamma E2, gamma E3. Okay, this was E1, E2, E3, and this is the vertex. Okay, we said that the sum of these contours is 0 because you can close it from behind the surface. Now, if this is the case, that means that the product S gamma E1, S gamma E2, S gamma E3 is the identity matrix. Okay, now you take this expression, you deform it, and okay, so what you get is, so let me write it this way, so you have basically the product of E to V S gamma E is equal to the identity. Okay, this is non-commutative, but you pick the natural order in the product. Okay, and now you can calculate delta of this, which gives you that the sum of okay. This is not very convenient to write, but somehow I hope what we're doing is kind of clear. So okay, so we had S1, S2, S3 equals 1. If you deform this, you get delta S1, S2, S3 plus S1, delta S2, S3 plus S1, S2, delta S3 equals 0. Okay, now you can basically notice that S2, S3 is S1 inverse. This is S1 inverse. S1 times delta S2, S3 is what? So basically we want to write S2 inverse. Okay, so S1 inverse was S2, S3. Now S2 inverse is the inverse of, okay, so S2 is S1 inverse, S3 inverse, inverse. So this is S3, S1. Okay, so that means that this here is S1, S1 inverse times delta S2, S2 inverse. S3, S1, S1 inverse, okay. And now this one here is it's basically the same, so it's going to be S1, S2 times delta S3. Okay, so S3 inverse is S1, S2. So this is now S3 inverse times S1, S2 inverse. Okay, so now this is not quite what we had here. Okay, and the reason for that is is that so some vertices yeah, okay. Of course, it's because E has an initial point and an end point, okay? And at the initial point, you keep the same, but at the end point, you have to parallel transport it, okay? Which means that here it was not well written, okay? So there are some conjugations happening. So yeah, okay, so this is a mess. All right. So how can we get that back? Delta S1 dot plus this is equal to 0.
Use a trace that not you cannot do the same step of projecting on the basis. Maybe you have this invariance.
You mean that okay, because this is the cycle, so basically you can integrate it, or you can integrate forms on it. Yeah, but to integrate forms on it, you need to check first that its boundary vanishes. Otherwise, the integral might not be defined. So that does not work, but thank you. The point is
pull back to the same base point on this cycle, and then you have to conjugate. The second thing is supposed to be at the start of gamma E2, and then you have to first pull it back to the start of gamma E1. So that's what the S1 conjugation does. The last one, it was at the start of gamma E3, and you have to pull it back along the first two cycles.
Yeah, in order for them to be at the same vertex. And so this is the reason why here you would have additional conjugation. Well, that makes sense. Yeah, okay. Does that make sense to everyone? Yeah, Alessandro buys it. Okay. Yeah, so somehow Okay, so this is what happens at every vertex. This relationship here is correct. Now the point is when you have an edge, right? So if you have the edge E3 or E1 here, okay, when the okay. Well, okay, all right. Okay, give me a minute. Because this would then define a map from the deformations of the setup of the quantum spectral curve into the space of cycles, the H1. All right, thank you. The sure. That being said, yeah, okay, let's do this. All right. But somehow I'm troubled by this, right? So okay, let's just assume that, and I'll come back to this later. I'm just going to erase that actually. Okay. Okay, so assuming we're able to write the boundary of this correctly, using the kind of equality that we have here, it should be 0. Okay, so if this is the case, then we have this map that associates deformations a cycle in H1. Okay, and so basically this this map is almost invertible. Okay, it's not invertible because there are some elements here that do not have pre-images, and these elements are the first kind of cycles that we had described yesterday. So these were when you are close to one of the poles, right? You could have a path on the base, which is this one, the gamma, say 1 here, and this would be in H1 hat as soon as, so gamma 1 tensor E, right? This was equal to 0 as soon as E belonged to the centralizer of the monodromy around that edge. Okay, and these, for the external edges, are the cycles that you cannot obtain from this construction here. Okay, but for the other ones, you can define a variation of the data, so say d sub gamma, right, of phi, to be equal to, okay, this is d f of gamma plus a commutator f of gamma with phi. Okay, so this defines, so conversely, it's going to be on the second line. It's going to be on the next line. So conversely, if gamma is in h1 hat of nabla mod the direct sum of the gamma j's from j equals 1 to m tensor the centralizer of the monodromy around gamma j. Okay. You can define d gamma of phi in such a way where f of gamma is the integral on gamma of m. So here, right, this is a linear combination of chains downstairs weighted by matrices. So points here are actually of the form x on the base, comma, a certain matrix. Does that make sense? Because you need a point on the chain downstairs. And since this gamma is the linear combination of chains tensor the matrix, if the point is on one of the chain components, then you just pick the matrix that corresponded to that chain. So that means that so x comma e, if this if gamma takes the form is a linear combination like this, so this gamma say you have some gamma I tensor e, or rather fi for some matrix, maybe not f, so e I. Okay, then if little x belongs to that chain here, then the corresponding e has to be the ei, the corresponding ei. Okay, and then f gamma is the integral on this one of m of x comma e divided by so here I put an x, and here I put, say, a y, and this is just x minus y d y. No, it's y. It's y. Okay, so it's so this is the deformation where f takes this form. Okay, matrix valued differential form, and you integrate it on a gamma. Okay, where gamma is part of h1 hat, but you've modded out all these cycles at the external edges. No, m is the solution of the differential system. So it's just a matrix valued function that depends linearly on E. Right? So it's a matrix valued function of y, and it depends linearly on this matrix E. You just can't get these things. Right? It's as simple as this. It's just that the form of that can't be of this form. Okay. All right. So yeah. Uh-huh. Yeah, you define the deformation in such a way. D gamma of phi.
It's a subjective map onto that quotient.
It's actually a bijective map on that quotient. Yeah. This. Right?
So that's D gamma R. That's an inverse map.
So D gamma is delta.
Yes, exactly. So maybe here delta gamma should be more right. So you have gamma delta and delta gamma, right? Okay. How long do I have left? Okay, perfect. So okay, so basically the idea is that you see that this equation here, it kind of looks like a zero curvature equation. Okay, so you put everything on the same side, you get something of the form delta gamma minus f gamma commutator with d minus phi is equal to 0. Okay, so this hints at the fact that psi, right, that psi, which satisfies d psi is phi psi. Okay, so this is the same thing as phi being d psi psi minus 1. Okay, so this tells you, since we're looking for an f that satisfies this zero curvature equation, that you want to define f of a certain deformation as del psi psi minus 1. Okay, so f gamma should be related to psi in such a way. Okay? All right, so if you do this for any deformation, right? So let's define f delta in such a way. Okay, then you can use the Cauchy residue formula, right, to write in general f delta of x minus, say, so basically as, just write the residue at y equals x of dy over y minus x times f delta of y. Okay, so now that we write this in this way, you can take this little contour, push it to the boundaries, to the boundary of C gamma, okay, and write this F delta as a sum over the edges of the graph. Okay, so now you get this as 1 over 2 pi I. Right, because in French we say 2ip. Right. Anyways, so 2 pi I in English of the sum over the edges of epsilon of the integral of e plus minus e minus, right, for the same reason as before, of the integrand that we have here. This is dy over y minus x f delta of y. Okay, but now we can use that definition here to calculate the difference that f delta has on one side and the other of a certain edge. So this gives f delta of gamma dot x minus f delta of x. Okay, and so you replace here. So this is now delta psi of gamma dot x, psi of x minus 1 with a gamma dot x minus delta psi x inverse. Okay, now psi of gamma dot x is by definition of the monodromy matrices psi of x times the monodromy matrix. So if you do delta of psi gamma dot x, this is now delta of psi x is gamma. So this gives you two terms, delta psi of x times s gamma plus psi of x dot delta of s gamma. Okay, so if you multiply this by psi of gamma dot x inverse, right? So you get delta psi x times psi x inverse, okay, which will cancel with this one. Okay, plus psi of x times delta s gamma minus 1 psi of x inverse. Okay, now this integral can be separated in the integral over e plus minus the integral over e minus. This thing here has the same value on both sides of the edges, and this one has this value on one side and this one on the other one. Okay, which means that this integral can be rewritten as 1 over 2 pi I sum over the edges of the integral over e plus of dy over y minus x, and now we only have this one. So psi of x something psi of x inverse, but this is m, right? We had this m here, y dot e. This was psi of y e psi of y inverse. So here this is m of y, because it's a y here, dot delta s gamma inverse. Okay, and this here is exactly that, with gamma being this. All right, which implies that f delta of x is equal to so the integral of my dot e or y dot e inside of gamma delta up to 2 by I. 2 by I over y minus x dy. Okay? All right? So this is how you relate this gamma delta to this f. Okay, are there questions about this? Right, so it's basically the same kind of techniques that we used in the Riemann bilinear identity. You have some kind of integral, push it to the boundary, you have e plus, e minus, calculate the monodromy when you go on one side or the other of the edge, and then put it all together. Okay. Clear? All right, so let's erase something else. Okay. Okay, so now what happens if we deform W1? Okay, so W1, x comma e, that was a trace of phi of x, m of x comma e, like this. All right, so this now you can deform it, calculate delta of W1, okay, and I'm going to spare you the calculation because so actually I don't have time to do it. Okay, but the idea is that okay, the idea is that this delta of W1, you can write it as a certain linear map acting on gamma delta. Okay, and this b hat of gamma delta is defined in the following way by b hat of gamma. So what is this b hat of gamma? Right? It's a deformation of something which is a linear form on the matrix E and defined on X. Okay, so if you deform it, right, you don't change the nature that it's a one form in X. Okay, and since it's a linear deformation, you keep something which is again linear in E. Okay, so you again have a matrix valued one form. Okay, and if it's a matrix valued one form of the same type, then it will basically take the same kind of input. Okay, and this now takes the form of, so it's the integral of x prime e prime inside of gamma, where gamma is this one. Okay, and now you have the trace of m x comma e m x prime comma e prime divided by x minus x prime squared times dx prime times dx okay, but that's not it. There's a second term. Okay. And that second term is minus the trace of the commutator of phi of x with m of x prime e prime times m of x comma e, and all of it times dx prime, and divided by, now I have to get this sign right, x prime minus x. Okay, so this is a direct computation. So close here. It's in phi, but indeed it's a one form in x. Okay, so delta of W1 takes this form, b hat of gamma delta. Gamma delta is this guy on the left. And now we have b hat of gamma x comma e that takes this form. Okay? It's a direct computation. I encourage you to do it. Okay. The difficulty is to understand why there's a term to remove. Right? Because if you just take the if you just say, okay, I'm going to differentiate the evaluation of W1, then you're just going to get the first term. But we're not deforming the evaluation of W1. We're deforming the map W1 itself. Okay? So if you apply, so if yeah, okay. So that's the remark. Okay. Now, b hat of gamma is a matrix value differential form, and what you can show, and actually in a very reasonable way, which is not too complicated, is that the integral of b hat of gamma 2 over gamma 1 minus the integral of b hat gamma 1 over gamma 2 is equal to 2 pi I gamma 1 intersected with gamma 2. Okay, so the way you do this is by replacing b hat gamma. This is this expression. So you have double integrals. These double integrals, those that have a simple pole, that part with the simple pole doesn't contribute. And the part with the second order pole actually exactly counts the intersection. So if you now take into account the fact that you have these weights here, you exactly get the generalized intersection. Okay? All right. So now, and I will conclude on this. The idea is that if you have a family of quantum spectral curves, or a family of matrix value differential systems, you can define a one form on that family. Okay, so if you have So you can define a one form on a family of quantum spectral curves, okay, by omega, right? So it's a one form, so it takes a tangent vector and gets you out a number, right? So say basically it takes as an input a deformation and gets you out a number. And so omega delta can define a one form as omega of delta being the integral of W1 over gamma of delta. Okay? Now this equation here tells you that this one form is not closed. Okay? And it tells you exactly that its curvature is the intersection form. Okay? Which means, so let's put it this way. So this is d, so the exterior derivative of omega okay, so it takes this time two deformations, so delta 1 and delta 2. This is equal to 2 pi I gamma of delta 1 intersected with gamma of delta 2. Which means that if you fix a Lagrangian subspace inside of that quotient and you pull it back by the map between deformations and cycles, then you get a Lagrangian in the deformation space of your family, on which, by this equation here, the one form is closed in such a way that you can integrate it, which means that you can define, so if you fix the Lagrangian, so L, Lagrangian inside of H1 hat mod these gamma J's tensor centralizers. Okay, you can pull it back. So by the map gamma, so gamma star of L, and if you restrict d omega to this is 0. Okay, which implies the existence of a function, say curly f of that Lagrangian function on a subfamily that integrates the Lagrangian such that, my time is up, such that d of fl equals omega restricted to the somehow the subfamily. Corresponding to the Lagrangian. Okay, I'm being a little quick here because I'm out of time. But this function here is the logarithm of the partition function of the topological recursion you would obtain if you introduce an h bar and do the h bar to 0 asymptotics. Okay, in the cases the asymptotics are nice enough that you can reconstruct them by topological recursion. Okay, so okay, sorry I had to be a little fast here, but so I'll end here, and please come with questions at the exercise session, and we'll see some of the details and the things that I've skipped, and a little bit more in-depth stuff this afternoon.
what you would call W2.
So yeah, W2 is this first part. Exactly, only the first part. Which is a little confusing, right? But you get used to it. And somehow the second part is, so that's exactly the difference between deforming W1 and deforming the evaluation of W1 on a certain point, right? And so somehow if you deform the evaluation, you get W2 directly, but somehow this is not what you do. So you need to add this like correction term to make it into something that you can actually integrate there. Oh, yeah.
So there'll be a version of the WGN.
Yes, exactly. So
Potential.
B hat is related to W2, and you see it's like a trace of products of M with a double pole, and the WNs for higher ends, they will be defined in a very similar way as some combinations of traces of products of M over some cyclic products of the points at which you evaluate them. Okay, but we will see that this afternoon. Yeah. Yes.
I've got many questions, but
Feel free. Yeah.
so each by somehow floating around in this fantastic.
I mean, here it's equal to 1, and that's the point. Is that somehow you can do everything non-perturbatively without considering h bar.
Oh, yes, okay. But you can introduce it.
Yes.
And expand following those formula that you give.
Exactly.
And then you say that h bar is the same as h bar that appears in the question.
Yes.
Okay, so it's not like the data thing.
No.
Okay.
Yep. So this f is the logarithm of the partition function, right? And this partition function that you obtain by if you want exponentiating this function f, you can show. So once you introduce some WNs, you see that these WNs satisfy a non-perturbative version of the loop equations, and then you can prove that these loop equations are equivalent for W constraints for the exponential of f. It's the free energy. Yeah. The exponential of the free energy is the partition function. And the partition function is a W conformal block. Mm-hmm. So of f.
Also, I mean, I assume also when the loop equations and the constraints that you say, these things will also have this.
So yeah, I mean, somehow the question you're asking is kind of deep, because here we have a certain action that we can cook out of the W algebra, which is not the one you're thinking of.
But that's why I'm asking, like, what happens if I take the limit of h bar goes to 0, and really like I assume it's a follow or whatever, so that like everything makes sense. Then what do I get for the W constraint?
Well, you get topological recursion.
But topological recursion, not topological recursion, you just work for the
No, of course. You need the WNs, because, no, but the thing is that here, okay, basically the construction goes as follows. You need to build these WNs. These WNs, they satisfy loop equations, and then you need the whole tower of loop equations to define a vector in a certain Fock space that is annihilated, that is a highest weight vector, if you want.
But that will involve
all the WNs. Exactly. This way you construct a vector, right? And if you want the overlap of that vector with some ground state, will be the partition function. Does that make sense? Okay, you're welcome. Yes. Yeah. Yeah. So basically, the whole point is this map, right, between deformations and cycles. So if you add more moduli, you have more deformations, and you need to add the corresponding cycles. And if you add the corresponding cycles, the whole story follows. So you can do higher order poles, higher genus Riemann surfaces, and deform everything you want. And it will fit in that way with that picture here, right? Which means that this is the exterior derivative on your family of differential systems, okay? Which means that it takes into account all the moduli that you have. What? Yeah, but which one? So some tau functions, yes. Some tau functions, yes. And by the way, I wrote it in this way, deformation way. Definitely. I mean, you see, this is d log, right? So if you do d log, we know exactly that they should be proportional up to some functions of something. And so, yeah, it would be very interesting to compare indeed.
And they can see the deformation or these times.
Yeah.
Do you have the map between your cycles these times?
Yes.
You can have it explicitly.
Yes. Even considering irregular types of your connection with Stokes data, these fit also in that framework. So you have cycles that correspond to little arcs in the real blow up around your irregular singularities, etc., etc. And you can write all of this down explicitly.
I guess we can.
Sure. Yeah. Thank you. No, you're welcome.